In this section, we would highlight the spatial representation methods and their significance, highlighting the spatial information and cartography, where the focus would be on the presentation and depiction accuracy of spatial information. Maps still remain an excellent way of compiling spatial information. There is no doubt about it. It can be designed to be easily converted into digital format. For example, by the use of different colors which have distinct signatures, and when they are being scanned by electronic sensors, they may give good results. However, consistent, accurate retrieval of information has become a great challenge in modern day world. When we are digitizing, when we are using the older spatial information, converting it into digital format, there are some errors which are bound to come. We need to take care of it also. To elaborate the digital spatial information and computer cartography, I would say digital spatial information has a primary goal of producing analog maps or analog images. Systems have advanced tools for layout, placement of labels, large symbols and font libraries, interfaces for expensive, high quality output devices. However, it is not an analytical tool. Therefore, unlike data for geography, cartographic data does not need to be stored in ways which allow, for example, analysis of relationships between different themes such as location and evolving transformations, etc. So the volume of information for spatial information might be much lesser than the volume required for geographic information. That is where I would say one big difference lies with geographic and spatial information data. The spatial data stored in digital format allows for rapid access for traditional as well as innovative purposes. The nature of spatial information creates difficulties when used as a source for digital data, but most spatial information takes no account of differences between datasets derived from maps at different scales. And the generalization procedures in spatial information become fixed to the data derived from them. Now, the scale in spatial information. With spatial information, the traditional concept of scale in terms of distance does not apply because digital maps do not remain fixed in size. They can be displayed or plotted at any possible magnification. Yet we still speak of the scale for a digital map also. In digital spatial information, the term scale is used to indicate the scale of the materials from which the image or pictorial depiction was made. For example, if a digital spatial information is said to have a scale of 1:1 lakh, it was made or it was obtained from a 1:1 lakh scale paper map. However, a digital spatial information scale still allows us to make some educated guesses about its contents because generally digital spatial information retain the same accuracy and characteristics as the source map. So it is still true that a large scale spatial information will usually be more accurate and less general than a small scale spatial information. It is quite obvious also because the display size of a computer based information is not fixed. Users are often tempted to zoom in to have a larger size of the phenomena. For example, as we have said, 1:1 lakh scale map can easily be plotted at a size of 1:24,000 or even to 1:2,000. But it usually carries some distortions when we are transforming the scale, changing the scale. So, spatial information with appropriate scale are suitable for depicting desired phenomena. At smaller scales, large scale data are too complex but can be generalized. On the other hand, at large scales, small scale data are too generalized where detail cannot be added. You can see in this image, in this slide, that how the scale, when the scale changes, the shape and size is changing, and how the jagged line, they are being simplified. As scale is reduced, fewer elements, fewer details can be displayed. Area features in large scale becomes point and lines in small scale map. Like a city or river in large scale becomes point and line respectively in small scale maps. The spatial information resolution, which refers to how accurately the location and shape of represented features can be depicted for a given scale. Scale affects resolution. As scale decreases, the map resolution diminishes because features are be smooth or simplified or even not shown at all. The spatial information accuracy. There are many factors besides resolution influence how accurately features can be depicted, including the quality of source data, the map scale, and skills of the creator also. In addition to this, human drafting errors can be compounded by the quality of our source maps and materials. The spatial information may be accurate for one purpose, is often inaccurate for others, since accuracy is determined by the need of the task as much as it by the spatial information itself. Some measurements of spatial information accuracy can be, for example, absolute accuracy of a spatial information refers, the absolute accuracy of a spatial information refers to the relationship between a geographic position on any representation of spatial information. For example, a street corner for example in any geographic representation, and its real world position measured on the surface of the earth. The absolute accuracy is primarily important for complex spatial information, such as those for surveying and engineering based applications. Another can be the relative accuracy, which refers to the displacement between 2 points on a spatial information, both distance as well as angle, the direction, compared to the displacement of those same points in the real world. The relative accuracy is often more important and easier to obtain than absolute accuracy because users rarely need to know absolute positions. More often, they need to find a position relative to some known landmarks, which is what relative accuracy provides. Users with simple data requirements generally need only relative accuracy. Another can be the attribute accuracy. Attribute accuracy refers to the precision of attribute database linked to the spatial information features. For example, if the spatial information shows land use classification, so how correct or accurately they are existing over the Earth's surface. The attribute accuracy is most important to users with complex spatial information requirements, where we are synthesizing the many spatial information. So their attribute accuracy is very important and critical for analysis. The spatial information currency, which refers to how up to date the information is depicted. Here the time dimension comes into the spatial information. This currency is usually expressed in terms of a revision date, but this information not always easy to find. A spatial information is complete if it includes all the features and users would expect it to contain. For example, does a street map contain all the streets? The completeness and currency usually are related because a map becomes less complicated and complete as it gets older. Because the older map may not have the newer roads in the map, and if the improvements have been made into the roads, they would also not come in the road map, so it wouldn't be complete. So here the map currency would play a very important role in depicting the spatial information, and it has great relevance also. The most important issue to remember about spatial information accuracy is that the more accurate the information, the more it will cost in time also, and it will be also expensive to develop. For example, digital spatial information with coordinate accuracy of 100 km can be purchased very inexpensively, or might be you may find openly in digital format. Many of the satellite images are easily available without paying anything, but these are having crude spatial resolution. But if you go for good scale, good spatial accuracy information, for example 1 meter accuracy is required, if the acquisition cost may be very high. So this is the difference between the spatial spread of geographic space and its acquisition and the cost related with it. The spatial information extent is very important and critical. The aerial extent of spatial information is the area of the Earth's surface represented on the spatial information. It is the limit of the area covered, usually defined by a rectangle, just large enough to include all the required features of that specific geographic location. The size of the study area depends on the spatial information scale. The smaller the scale, the larger the area which would be covered. For example, here in this slide you can say all maps are modeled representation of the real world, and therefore the features are reduced in size when mapped. Here easily one can understand the difference in details of information. A standard book map representation on board with 6 feet by 8 feet dimension, or 2 inch by 3 inch pictures. With change in scale, a river can appear as line, or a city may be represented as point, if you can see this slide on the right side image. So map scale determines the size, shape, and above all the details of the feature represented in any map. Another feature of the map is the database extent. It is a critical first step in building a spatial information database is defining its extent. The spatial extent of a database is the limit of the area of interest for the project. This usually includes the area directly affected by the assigned spatial units as well as surrounding areas that either influence or are influenced by relevant activities in the given area. The next can be the spatial information automation. The spatial information features are logically organized in a set of themes of information. A base map can be organized into layers such as roads, soils, land use, land cover, or state boundaries, etc. The spatial information, regardless of how a spatial database will be applied, is collected, automated, and updated as series of adjacent geographic spaces. And in order to able to combine these smaller spaces into larger units or study areas, the coordinates of coverage needs to be transformed into a single common coordinate system. And once in a common coordinate system, attributes can be associated with the geographic features existing over the Earth's surface in that specific study area.